Continuing from the last lecture, let us take another look at this two-dimensional crystal. So, I have this lattice whose translation vectors are A and B. Now, in this crystal, let me add, let us call this as atom A, and let me add coincide the center of the atom with the lattice point. Now, how can I describe this crystal structure? So, way we can describe it, we describe the lattice first. So, lattice is described by essentially the vectors A and B, and the motif has to give the position of the atom with respect to each lattice point. So, in this case, I will put the position of atom A at 0, 0. What this means is that we draw a vector from the lattice point, from every lattice point to the position given in the motif, which is 0, 0, which essentially means that the atom would be placed on the lattice point itself. Now, imagine that I have another atom, let me call that as atom B, and its position is at some location x, y with respect to every lattice point. So, what this means is, suppose this x, y could be somewhere here. Basically, what we are doing? We are drawing a vector from the lattice point to the position or the end of the vector at x, y. And we will do this for every lattice point, and this is how this atom B would get positioned. So, we draw the same vector from each lattice point. So, there is no ambiguity here. Atom A is located at 0, 0 with respect to each lattice point. Atom B is located at position x, y with respect to each lattice point. Now, just like we have unit cell for the lattice, we use the same unit cell for the crystal now. So, this is my unit cell defined by the parameters A and B, the vectors A and B. So, if I now look at it, now this was a primitive cell in the lattice, this still remains a primitive cell because it has one lattice point per unit cell. But now, how many atoms do we have here? If we had only motif consisted of only one atom, then very clearly the atom A, which is located at the corners of the unit cell, gets shared by 4 other unit cells, and hence 1/4 contribution of that atom A would be there in the unit cell, and there are 4 atoms at the corners. Hence, I will have one atom. So, one A atom per unit cell, and now if I look at the B atom, you can see that out of the 4 B atoms, one atom is completely inside the unit cell. Hence, I have one B atom per unit cell. So, total I have 2 atoms in the unit cell, one A atom and one B atom. Now, if I have to look for lattice parameters of the unit cell, so how many lattice parameters do I require to define this unit cell? I need the magnitudes of the vectors A and B, and I need to know the angle between the two vectors, which if I call, let us say, as alpha. So, I have total of 3 lattice parameters in the unit cell. So, by defining these parameters A, B and alpha, I define the unit cell of the lattice, and that also will then become the unit cell for the crystal structure after I add the motif to the lattice points. Now, just one little thing that I think can be appreciated now, that this motif that I have can be replaced by literally anything. For example, let us again consider a lattice of points. And let me take a very different kind of motif, not an atom. Let me take this motif in the shape of the letter L, and it will have some coordinates x comma y as the one such symbol at x comma y. So, it could well be the position here. So, I have a pattern. Instead of having atoms here, I have simply put this particular symbol. One can do create some other pattern. Let us say I take this kind of a pattern. I can populate this motif at all the lattice points. Again, some location, maybe this point that I have put here is the center from where the x y coordinates should be measured. So, then maybe I have, so this is at again x comma y, and so I draw vectors from each lattice point and locate the motif at every lattice point. So, essentially what I have done, I have simply created some patterns out of this. And in particular, I would say crystallographic patterns. So, in essence, what is crystallography? Crystallography is a study of patterns, and by studying these patterns, we also are understanding the development of crystals where atoms are present. And many times by using these patterns, they are useful to understand crystallography in better detail, as we will see later on in the course. I could also, for example, if I look at the first pattern, I can create maybe now a motif something like this. So, I have now two entities there. So, now this one is let us say located at x1 y1 and this entity is located at x2 y2. So, again draw the vector to x2 y2 and put the second element of the motif. So, I have created a different kind of pattern in this case. Now, how is it different? Let us try to understand this, though we will be delving in great detail later. We have only looked at translation symmetry so far, but there are other symmetry elements that would also come in. So, for instance, if I now look at the same lattice, I will draw a separate figure here. One of the symmetry elements that we will look at among others is that if I draw a line here, this is a reflection symmetry. So, I have basically drawn this line represents a mirror plane, and as you can see that this mirror will reflect the lattice points on top of themselves from either side of the mirror. So, this lattice point will get reflected out here, this one will get reflected out here. So, in the sense there is mirror symmetry in this, and you will also see that there is a mirror here as well, and therefore, there is going to be just like the lattice is infinite, there are going to be infinite number of mirrors here. But now, I look at this pattern. Here you will notice that there is no mirror symmetry, because I have two different elements. So, there is no mirror either going through the lattice points or in between the lattice points. So, this is also a mirror which is in between the lattice points. And in fact, if you will notice, there is a mirror here as well, there is a mirror here as well, there is a mirror here as well. So, these are all mirrors, but in this structure all the mirrors are gone. So, there can be a big difference. The lattice may have a lot of symmetry, but once you put the motif in the lattice, a lot of that symmetry may be missing. And this is important to understand, because this is the reason why a lot of misconceptions arise, as we will be seeing. So, in a nutshell, crystallography is a study of patterns, and I now want to extend the idea of a lattice and a crystal to the third dimension as well. So, let us look at the lattice in 3 dimensions. So, lattice in 3 dimensions, let us understand what kind of a unit cell, because it is difficult to draw the points, lattice points in 3 dimensions. So, let us just look from the perspective of a unit cell. So, a unit cell in 3 dimensions, in 2 dimensions, all unit cells are some form of parallelogram. Okay, some of them may be very oblique, while others may look like a square or a rectangle, but they are all parallelograms. In 3 dimensions, we will have what is called as parallel piped. So, drawing this thing, let me try to draw this. And let me put these axes x, y and z. So, this is a unit cell in 3 dimensions. Where are the lattice parameters? Just like we had A and B as a lattice parameter in 2 dimensions, and the angle between those two vectors A and B as alpha. Now, we are going to have many more lattice parameters here. So, I have lattice parameter this vector A along x, vector B along y axis, and vector C along the z axis. So, I have first of all 3 length parameters A, B and C instead of only 2 in the case of 2 dimensions. And what are the angles? We also have to specify. So, angle between B and C, we call it as alpha. Between vector C and A, we call it as beta, and between A and B, we will call this as gamma. If you notice something interesting here, so these are what we call as conventional parameters to use. So, between B and C, I have the angle alpha. So, you can see that we use Greek letters for the angles in the same order as A, B, C. So, I have the first 3 letters in English is A, B, C, the Greek letters alpha, beta, gamma. So, B and C, A is the missing vector. So, I put this as alpha. Between A and C, where B is the missing vector, I have beta, and between A and B, the angle is gamma. So, there are total of 6 parameters, 3 length parameters A, B, C, and 3 angle parameters alpha, beta and gamma. Basically, based on that, you construct different kinds of unit cells. So, I am going to now compare the unit cells in 2 dimensions with the unit cells in 3 dimensions, and later we will actually derive these unit cells, why we have these specific unit cells that are given. So, consider first 2-dimensional unit cells. One is called oblique. They are all parallelograms. So, one is called oblique. This has that A, B and alpha. So, they have 3 parameters here A, B and alpha. They are all unrelated. So, A and B have no constraints. Let me put it this way, A and B no constraints. In fact, even alpha has no constraints. So, A, B and alpha can take any kind of value that is possible. A second lattice is called rectangular, or I should say, actually I should add the word primitive as well. So, there would be primitive. Second one is called primitive rectangular. Third one is called centered rectangular unit cell or lattice. Fourth one is called square, primitive square. And fifth is hexagonal. I will come later as to what kind of constraints each one of the lattices put on the parameters A and B. Now, let us look at the 3-dimensional unit cells. Just before that, primitive oblique obviously very clear, all the lattice points are at the corners. Primitive rectangular, all the lattice points at the corners of a rectangle. Centered rectangular means lattice points at the corner and one lattice point in the center. Primitive square, again only lattice points at the corners of the cell. Hexagonal is also primitive. So, lattice point only at the corners of the unit cell. I am deliberately not trying to define these unit cell more than this. We will be coming to this pretty quickly in this course, where you will see how we define the lattices and what is the basis of defining the different lattices that we have. So, three-dimensional unit cells, where can I put the lattice point on this parallel pipe? Well, one place I can put lattice points, obviously corners. By doing this, I am forming a primitive unit cell, and once I translate this unit cells by A in the x direction, by B in the y direction and C along the z direction, I will get the entire infinite lattice. So, that is one. So, I will form a primitive lattice. What else can I do? In addition to the, so these are lattice points only at corners, and the other thing I can do, and still it remains a valid lattice, which means it follows translation symmetry. So, in addition to lattice points at corners, I can add a one lattice point at the body centered position. So, I have lattice points at the corners and I have lattice points at the one lattice point at the body centered position. Another alternative I have lattice points at the corners plus centers of two opposite faces. A third option that I have is centers of all 6 faces of the parallel pipe. So, what I have described right now is 4 different classifications here. One, primitive, lattice points only at the corners, and lattice point in the body centered position plus corners, centers of 2 opposite faces and corners, and center of all the 6 faces of the parallel pipe plus corner. And you can clearly see, if I have to look at how many lattice points are going to be there per unit cell, here of course I will have only one. Out here I will have one for the corner and one for the body centered position, which is 2 lattice points per unit cell. Centers of 2 opposite faces. What does this mean? That I have put a lattice point, let us say I can take this top face and at the bottom face, then each of these lattice points will be shared by 2 cells, hence half a contribution of each of these 2 lattice points to the unit cell. So, I will have again one contribution coming from 2 opposite faces, again 2. If I look at the lattice points for, in this case, 6 faces and the corner, so I will have 1. From each face I have half, and I have 6 faces, so 6 into half, and which makes it 4. So, essentially I have defined these 4 classes, or you can say 4 different ways I can put lattice points without violating the lattice condition, which is that all lattice points must have translation symmetry. Finally, I will leave you with one question. consider a unit cell consider this unit cell and let me put lattice points again at all the 6 corners, all the 8 corners, and I will put lattice points only, let us say, on this left face, on the right face. I will put it in the front face here, at the back face. Then, so I have essentially put 4 lattice points, 4 additional lattice points on the kind of vertical faces, and I have put no lattice point on the top face and the bottom face. So, I have essentially added basically corners plus 4 on centers of vertical faces. Is this allowed? Well, the answer is no to this, because this will violate the translation symmetry, or that every lattice point must have identical environment as we had discussed in the last class. And I will leave this to you to verify it that this is indeed not a lattice.